Alright, so we had the last quiz before the exam was due yesterday at midnight. If you haven't taken it yet, you can still take it for partial credit. It was the chapter 4, part 2 quiz, all about energy and power. For Sunday, what's due is the exam. So what we're doing today is we're reviewing for the exam. Now the exam's covering 3 chapters, so it's a bigger exam, it's more questions. So it's going to be 50 questions, 49 of them are multiple choice and 1 is fill in the blank. But for the most part, multiple choice. And then it's actually 51 questions because there's 1 bonus question at the end, just worth 5 bonus points if you want to give it a try. There is a 2-hour time limit this time. So last time there was 90 minutes. I just extended it since there's more questions. Now, not all of these questions are calculations that are going to take you 5 minutes. Okay, a lot of them are just concept questions. Best way to study, I put a practice exam out with an answer key. Please take it. That's really going to help you see what types of problems, what type of concept questions that you're going to see. I've also posted, which I've handed out to the people in class, an equation sheet that has all the equations you'll need on the exam. So chapter 2 through chapter 4, so that it's all in one place. Have this equation sheet ready when you take the exam. Have your calculator ready when you take the exam. Have any notes, PowerPoint's open or ready when you take it. I mean, it's an open note, open book exam, so make use of those. Don't depend on them 100% though, because you are going to need to know how to do these problems in order to solve them. You're not going to be able to look up this exact calculation online and get a straight answer. So what we're going to do in class today is I've made a review with just some sample problems similar to what you're going to see on the exam. So since we haven't looked at chapter 2 stuff in a while, we're going to start with chapter 2 and kind of work our way through. The exam should also be organized for the most part by chapter. So it's not going to skip from chapter 2 to chapter 4 and then back to chapter 3. I tried to keep it in order as closely as I could. So just try to make it a little easier to navigate. All right, so we're looking at, starting with chapter 2 problems again to review. We have number 1, a motorcycle accelerates from rest for a distance of 804 meters in 20 seconds flat. Okay, so the question is asking what's the acceleration, what's the velocity, a whole bunch of different questions. So what we need to do is approach it like we have been. Let's write our knowns and unknowns. Let's look at what type of equations that we're going to use. All right, so starting with that first step, knowns and unknowns. Look and see what you have. So what I'm seeing is distance of 804 meters and then 20 seconds. So that's 2 of my knowns. The 804 meters, that's going to be a distance. So I'm going to write that as my D variable. The 20 seconds, that's going to be my time. Now the first question is asking, what is the acceleration? So that's going to be an unknown, A. So how do I know what equations to use? Well, looking at the variables, when I see distance, when I see time, when I see acceleration, like that's all about chapter 2 and the velocity equations. Okay? Notice when we look at our velocity equations in chapter 2, we had 2 choices. We have 0 initial and non-zero, so 2 columns to choose from. So we look at words in the problem itself to figure out what type. So what's going to help me figure it out is it's saying the motorcycle accelerated from rest. So what that tells me is it was initially not moving, so initially 0. So I'm going to use my 0 initial velocity equations. Now if I want to solve for A, I'm going to look at those equations and I'm going to look at every equation that has A in it. So that's what I'm doing right now is I'm writing down every one. And then I'm going to compare it to what I have and see which one will work. So if you have 2 variables that are unknown, it won't work. What I mean by that, this first equation, velocity, no, I don't have it. Acceleration, No, I don't have it. So this equation will not work because I don't have two of the variables in it. So I cross that one out. The second equation, it's the same thing. Acceleration, velocity, no, don't have it. Now the third equation, distance, yes, 804. Acceleration, no. Time, yes. So I only have one variable that I don't know. So this equation works. I just need to rearrange it to solve for A. So that's what I'm going to do. I'm going to rewrite this equation. Right, D is equal to AT squared over 2. It's the same thing. I just put the A and the T in the numerator and left the 2 in the denominator. This is just going to help me rearrange it when I write it in that form. So the goal is to get A by itself. All right, so to get A by itself, I need to get rid of the 2. 2's in the denominator, which means I'm dividing it by 2. So to get rid of it, I want it in the numerator, so I'm going to multiply by 2. That way I get 2 divided by 2 cancels. Well, since I multiplied by 2 on this side, I also need to do it over on the other side of the equation. So it cancels here, and now I have 2D is equal to AT squared. Still trying to get A by itself. So that means I need to get rid of the T squared. Well, what I'm doing is I'm taking A and I'm multiplying it by T squared. So I'm going to do the opposite operation. Opposite of multiplication is division. So I'm going to divide by T squared. That way it's going to cancel. Whatever I do to one side of the equation, I have to do to the other. So now I have A all by itself. And to figure out A, I'm going to take 2D and divide it by T squared. Now I can plug in my numbers. I got 804 in for my D, and then the 20 in for my T. So it becomes 2 times 804 divided by 20 squared. And fortunately for me, it's only one sig fig. Portland, why you calculate that for me? Oh, my call. Sorry, I was pulling it up.
4.02.
4.02, so just one sig fig would be 4. And then the units are meters per second squared. I recommend that you take all of the variables and write a list of them and what their units are. Because then when you get to the exam, you'll have that list available to you. When you're going to pick an answer, you can be like, I just solved for acceleration. Did the choice I picked have meters per second squared? Okay. I actually give you that list on the first set of PowerPoints. And I have all the PowerPoints uploaded in a PowerPoint folder without audio so that you can just click from slide to slide and pick the slide you need for information that you want to write down or take notes on. So, yep, you will find that helpful, I think. All right, so let's look at the next question. What is the velocity of the motorcycle at the end of the 804 meters? So I'm going to leave this up. I'm going to write what my acceleration is in case I need it to solve for my second step. It's asking what is the velocity. So I'm going to look at my velocity equations. Remember, it's still 0 initial velocity set that I'm looking at, and I have V is equal to AT is one of my choices. Will that one work? I have A and T. So yes, it's the first one I saw. And it does work. So just plug in. We have 4 times 20. Yeah, that one I can even do. So my velocity is going to be 80 meters per second. They're really bugging it. All right. So now, part C, the last one, it's saying at this rate, so at 4 meters per second, how long will it take? So I'm going to erase this time because they're asking for a new time. How long will it take to reach 26.82 meters per second? Okay, so it took 20 seconds to reach 80. Now it's asking, how long would it take to reach 26? Okay, so we're calculating the time for a different velocity. So let's erase this velocity because we're not using that in this question. The velocity we're using is how long will it take to get to 26. So I'm just trying to show how to rearrange all the hard equations for the exam. So you want to do the same thing as you did before. We're using zero initial velocity. Write down all the ones that have time in it, and then see which one's going to work for you. That's just the rearranged version. Okay, so we have first one, distance, yes we have. Average velocity, no we don't. Time, no we don't. Get rid of that guy. Okay, and I forgot one, didn't I? Amy's going to do the over two. Right. So velocity we have, acceleration we have, time we need to figure out. So we have two of the three, so this one could work. That one is the same thing but rearranged, so that could also work. We have acceleration, we have velocity, we're looking for time. Okay, so either of these. We could actually even use that last one. The reason I'm not going to use that last one is because I have t squared. It's going to be a lot more confusing to rearrange than this one is. Okay, but either one would work. So I'm going to choose this guy. I'm going to rearrange it to solve for time. Let's see how long it takes at that acceleration to reach that velocity of 26. So it should take less than 20 seconds because it took 20 seconds to get up to 80 meters per second. And now we're not going quite as far. So let's see. To rearrange, I'm trying to get rid of the a. I want t by itself, so I'm going to divide by a on both sides of the equation. Cancels that out on one side. That gives me time is equal to velocity over acceleration. So I got my 26.82. And divide that by like 4. And it's only going to be 1 sig fig again.
So it's 6.7, so 7.
6.7, so 7 seconds. And as predicted, it took less than 20 seconds. So the answer at least makes sense. Right. So this is what you can expect for the velocity equations. I think there's only one problem using the non-zero initial velocity equations. So make sure you're taking that practice exam. I know there's a non-zero initial velocity one on there to help you practice. I also have those practice worksheets that I've posted for pretty much every chapter with the answers if you want more practice with the problems. So there's lots of opportunity study aids. It just depends if you use them or not. So we're going to look at next on number 2 are the vector problems. With vector problems, most important thing, make sure that your calculator is in degrees. If it is in radians, you're going to get it wrong no matter how you set it up. So for number 2, I'm just going to write the information because people in class have this handout and then it's also posted on Blackboard so you can print it or have it open if you want to see the whole question. But what they're giving us is 175 miles, so that's how far a ship is sailing, and it's sailing 35 degrees north of east. The question is asking how far east has it gone and how far north. So we need to know a few things about the vector, the problem itself, to figure out what these variables mean. So when we do vector problems, we use the XY axis. X being east, Y being north. So when it's asking how far north, what it's asking is, what is Y equal to? When it's asking how far east, what it's asking is, how far in the X direction. So these other two variables, this 175 miles, that's how far the plane went. This distance here. The 35 degrees, that's the angle at which the plane was flying at. So it's given us the 175 and the 35, and it's asking us to solve for this Y component here and this X component here. So to do that, we're going to use two of the four equations. And we want to pick the ones where X is equal to and Y is equal to. You'll notice on your worksheet, I have the vector problems. There's only four possible. When it's asking you to solve for east and north, you are solving for X and Y, so you will use the X and Y equations. This is A sine theta. Sorry, cosine is X. My bad. Cosine, and then Y is sine. This is the type you will see on the exam, where you are solving for X and Y. So make sure your calculator is in degrees. Okay? I'm not going to ask the other version, so if you can solve for these two, you're good. So now you need to plug in, well, what's A out of these two? So A is your 175. And notice on vector problems, it's the one problem in physics that we don't have to convert to metric. You can leave it in miles. Okay? So this 175 is your A. Theta, the symbol here, that's your angle. That's your degree sign. So whenever you see a degree sign, that's the theta. So you plug these in to that equation. So for X, you would plug in 175, you would press the cosine button, parentheses would appear, and you would write 35 inside of those parentheses, and then equals. You do the same thing for the Y, but instead of pressing cosine, you press sine, and then enter the 35. When you get these answers, they should both be less than your A value. That's kind of a check to make sure that it's actually in degrees. It might not be a lot less, but they're going to be less. Cosine 35. I'm getting 143. But I need two sig figs. So 140. And the units on it, they're asking distance in the X direction, and distance was in miles for A, so it's also going to be miles for the X. And then sine 35. Tell me if you guys are getting something different. I got 100. And that's impossible to do with two sig figs unless I do it in scientific notation. So I'm just going to leave it at 100. Is that what you guys are getting?
Yes, that's what I thought.
Yeah? Okay. So this is the exact type you'll see. You'll be given A and theta, and you'll solve for X and Y. And I think there's two of those on the exam, so make sure you know how to do them. There'll be words between 2 and 3 points apiece. I think 2 points. So 100 for the Y and 140 for the X. All right. So that takes care of the chapter 2 equations. You'll also see a free fall equation. I know I don't have one in the review, but there is one on the practice exam. So make sure you know how to do free fall as well. Free fall being an object falling and you use gravity as your acceleration. All right. So now moving on to chapter 3 problem examples. I kind of just tried to pick the harder ones to do during class. That's why I didn't do the free fall. Those are usually very similar to number 1 that we did, except you're using 9.8 for A instead of whatever they gave you for the acceleration. So number 3, most people find this one difficult just because it's a very long equation. So this one, you have 2 vehicles, center of their masses 7 meters apart, and it's the gravitational force. So this is that one where you are exerting a force on everything around you, and everything around you is exerting a force back on you. So these are those very tiny forces. We're using that equation. F of g is equal to g m1 m2 over radius squared, I believe. I have all these memorized by now. Yes, it is squared. Okay. So they're giving you 2 vehicles. So I have one vehicle with 1,800 kilograms. Kilograms being a mass. I'm going to label that M1 because I'm going to have 2 masses in this equation. So that's the key. They're giving you a second vehicle, and the mass of that vehicle is 1,500. I'm going to label that as my M2 for mass of second vehicle. Now, the masses are 7 meters apart. So the trick here, 7 meters, usually we would label this as a distance. But since it says, what is the force of gravitational attraction, they're asking for F of g. And when you go to look at your F of g equation, they don't have a distance, but they do have this R value. And that R value, it's still a measurement of length. It stands for radius. It's the radius between your centers of masses. But since it's a distance still, a length, you can use that 7 meters in for the R. Okay, either variable works. So for this equation, that 7 meters is the R variable instead of the D. Now the G, and that is a horrible looking G, but G, that's that gravitational constant, 6.67 times 10 to the negative 11. So this is given to you on the equation sheet right next to that equation. So you're going to plug that in for the G value. So don't forget this guy. You go to solve. Gravitational constant first. Plug in your masses, 1,800 and 1,500. Right? Yes. And then on the bottom, my radius is 7. Don't forget to square the radius. These numbers are generally, these forces are generally very small because of that gravitational constant. Yes, and I got a very small number. And my calculator does not put in scientific notation. So I'll get 1, 2, 3, 4, 5 zeros. And only one sig fig. Units on it are newtons. If your calculator gives it in scientific, it would say 4 times 10 to the 6, negative 6. Both of these are correct answers. Anyone getting something different?
You just rounded the 4.
I rounded it because it was
3-something.
3.6, I think. I already erased it, but it was 3.6 or something like that. Actually, let me think about it. Yeah, no, I can't look back. But yes, I did round it up because it was 1 sig fig. So moving to number 4, this is just a concept question. It's saying, while your mass is the same everywhere, explain why your weight may vary from place to place. So when I say your mass is the same everywhere, you need to look at definition of mass. So mass is the matter that an object is made up of. So you are made up of the same amount of matter no matter where you travel, unless you're losing body parts your mass, the amount of matter you're made up of, stays the same. It's your weight that varies. So why does your weight vary? Because in physics, weight is a force. Okay, so F of W, that's the weight force. And the weight force is dependent upon your mass, which doesn't change, but it's also dependent upon gravity. So gravity can change from place to place. So if you're on Earth, gravity is 9.8. If you're on the moon, gravity is 1.6 meters per second squared. If you're on Jupiter, I don't know what the value is, but it is different. Okay, so your weight changes depending upon gravity. So that's why it can change from place to place. So this concept you will be asked about on the exam, is why I wanted to pose it here. Your mass does not change, but your weight does. Number 5 is going to put that test to motion. So we are going to use that equation for number 5. We have an astronaut that's 80 kilograms. That's his body mass. He's wearing a spacesuit that is 92 kilograms. So once he puts his spacesuit on, his total mass is 172. Yes. We're going to calculate his weight when he is in his spacesuit and on the moon. Okay, so to do that, we need to know his total mass, which they gave us, it's him with his suit on, is 172. Now this wouldn't change no matter where he went. But when we calculate his weight, we're looking at a force, the weight force. We're using this equation. We know the mass. It's the gravity that is dependent upon where he is. And for this specific problem, we said he's on the moon. And we said gravity on the moon, you can also find that on your equation sheet. Gravity on the moon is 1.6 meters per second squared. So to figure out his weight on the moon, we're multiplying these two numbers. So 172 times 1.6. I think you have one like this. In your chapter 3 homework quiz, there's one like this on the practice exam. So you can bet money that you will get one like this on the exam itself. So he is 275. And since it's a force, the units are newtons. Okay, so this is where it's going to help you to make that list of all your variables. Force is always measured in newtons. Energy is always measured in joules. Velocity meters per second, acceleration meters per second squared, okay? Make a list with all the units because I will give you this for choice and I might try to trick you and give you like something funky. Or meters per second, who knows? Okay, so pay attention to your units. It's a force, so it's newtons, okay? I have to think of 4 choices, so sometimes I just change the units to add more choices. Yes?
Are we doing significant figures?
So this is the tricky part about this. Significant figures depends upon the numbers given in the problem. So the number given in the problem was the 172. That's the one we used, correct?
Yes.
And the number we multiplied by, yes, it has 2 significant figures. But this was not a number given in a problem. This was an exact number from the equation sheet. So that's why I kept it at 3. But I wouldn't count that wrong if you wrote it out and gave me 2 sig figs, because I know that that's a confusing concept. But on the exam, I'll most likely give you 3, just so you know why. And sometimes I make a mistake and only do 2 too, because I get caught up in the knowns and unknowns. So it's a mistake that I make as well as why I wouldn't count someone off if they did the same thing. All right. So we've covered weight force, linear forces, same equation, different A value. So moving on to impulse, we're looking at change in momentum. So remember, momentum was an object's mass and velocity. So we take the object's mass times its velocity to figure out its momentum. So number 6 is giving us a ball with a mass of 5 kilograms switching gears here yet again. 5 kilograms. That just said that's a mass. And that ball is traveling at 8 meters per second. So 8 meters per second. So to figure out what that is, it might be helpful to have your variables with the units, because you can just say, okay, which one of my variables has the units in meters per second? Velocity does. Okay? Then it says that same ball is slowing to 2 meters per second due to the force of friction. So they're giving me a second velocity. So since I have 2 velocities, I need to distinguish these somehow. I can label them as velocity 1, velocity 2, or as initial velocity and final velocity, whatever helps. I'm going to do initial and final because that's going to help the most for this one. So the ball was initially traveling at the 8 or the 2?
The 8.
8, that's where it started. So this is going to be my, I. Then it slowed down to a final velocity of 2. Calculate the impulse. So impulse is I, but what impulse is, the definition is it's the change in momentum. The final momentum minus the initial momentum. So when you're looking to solve for impulse, you would go find your impulse equations. That's why I have them headed, to help you find them easier. So under impulse, there's just 2 that you can use. Use your variables to figure out which one works. We don't have force, we don't have time, so it's not that one. So by default, that's the only one that's going to work. So then you can plug in your values. Okay, the mass, the m value, is the same here as it is here. So we're talking about the same object. It's the velocities that are different. So when we go to solve, we have our 5 kilogram ball. Its final velocity, so once it slowed down, was 2. We're going to subtract that from the mass of the ball, so the mass didn't change. And the initial velocity, what it started at, was 8, so before it slowed down. So for this one, we are going to get a negative number. That's fine. That just means the object slowed down. It's like deceleration versus acceleration. When an object slows down, the a value we get is minus, it's negative. When an object speeds up, the acceleration is positive. So the same thing happens here. This object slowed down, so we get a negative impulse, negative change in momentum. So we have 10 minus 40.
Yes.
One sig big to get negative 30. And the units. So to help you figure out the units on this, look at the units that you're multiplying. You're taking mass. What is mass? Kilograms. You're multiplying it by velocity. Units on velocity, meters per second. My units will be kilograms times meters per second. Same units that when we calculate momentum, since this is the change in momentum. Stop me if you have any questions, or if I'm going too fast. So, 7. We have a collision. A car at 18 meters per second rear ends a stationary truck. They lock bumpers and move off together after the collision. You get the mass of the car and the mass of the truck, and it asks us to calculate their final velocity. So, knowns and unknowns. We have a car at 18 meters per second. So 18 meters per second is a velocity. It hits a truck, they lock bumpers, move off together. The mass of the car is 1,600. So we have 1,600 kilograms mass. But then it's giving us a second mass, the mass of the truck. Okay, so I need to label these so that they're different. So the car, I'm going to label M1. The truck, I'm going to label M2. And the truck's mass was 2,200. What is their final velocity? what is the VF? So now before I go finding an equation, this velocity here, I need to label as either V1 or V2. So this velocity was the velocity of the car. So since I labeled the car as M1 with a sub 1, I'm going to label the velocity belonging to the car also with a 1. To figure out, so since we just said it was a collision, I need to look at my equations and figure out what type of collision it is. Well, notice on the equation sheet given for the exam, the only equation I give you is the inelastic collision one. Because the only time I'll ask you to solve for a collision is if it's inelastic. So if you didn't already figure that out by the fact that they locked bumpers and moved off together, you should figure it out by the fact that that's the only equation I give you to use for collisions. Okay, so you will be using this guy here. Or a collision example. Now remember, this portion is before, and this is the after. So before the collision, my M1, I have that. My V1, I have that. M2, that's the mass of the truck, I have it. Velocity 2, I don't have that. So what was the velocity of the truck before the collision? It says the car rear ends a stationary truck. Stationary meaning not moving. So the truck was initially 0. So I'm going to add that to my list for when I solve. Because now the only variable I don't have is my VF. This guy over here. And that's what I'm trying to solve for. And we've rearranged this a whole bunch of times already, but I'm going to do it again. This is a refresher. I want VF by itself, so I'm going to divide by this, the sum of the masses, so that it cancels on this side. And then I'm going to have to divide on the other side as well. Notice it's in parentheses for a reason. When you enter it in your calculator and you're adding those masses, make sure you put them in parentheses. So, my rearranged equation, I can plug in my values to solve for VF. So, I have 1,600 times 18. That is the mass of the car times the velocity of the car. Then I have the mass of the truck times 0, because its initial velocity we said was 0. Anything times 0 is just 0. Then I'm going to divide that by the mass of both vehicles added together. So 1,600 plus 2,200. And we are looking at 2 sig figs. So my final velocity in meters per second should be less than 18. Once that car hits the truck, it's going to slow down.
Is that how many? 2 sixes?
Yes, because I have 2, 2, 2.
So 7.6.
7.6, thank you. That makes sense because it slowed down from 18 to 7, making the truck speed up from 0 up to 7. All right. So, questions on this one? You might even want to write down the rearranged version because you are going to be asked to solve for final velocity. That way you'll already have it ready and you can just plug in your numbers. So looking at number 8, we're riding a bike. The tire goes flat and you have to push the bike the rest of the way with a force of 15 newtons. How much work is required? So we have to push a bike 650 meters. 650 meters being a distance or a height or a radius. It could be several different variables. It's it's a length. The force they gave us, so F, is 15 newtons. They're asking us to solve for is work. So when you look at your work equations, you have two. You have linear work and vertical work. So if you look at your equation sheet, it's under the energy equations because work is a form of energy. We have W is equal to FD, so this is the linear. What that means is if you're pushing something along the horizontal, along the x-axis, then you use this guy. The other one is F of WD, and this is vertical. You use this one if you are lifting something up from the ground, vertical, along the y-axis. Okay? Now this one, I'm going to write mgd. These are the same equation. Because what I did is I took the weight force, which is mass times gravity, and I plugged it in where F of W was. Okay? So you might want to write that equation next to the W equals FWD, because usually when you use it for vertical work, you'll be given the mass and the distance, and then you'll plug in the gravity as well. So which one are we looking at now? Linear or vertical? Tire went flat and they're pushing their bike.
Linear.
Yeah, they're not picking up their bike. So we're doing linear. So we're just plugging in our force and our distance. So we have 15 times 650. Two sig figs for this guy as well.
We get 9,750.
9,750?
Yes.
So 9,800. 750, we'd have to round up. Yes. Now units. So those energy equations, work is a form of energy. All forms of energy are measured in joules, J, after James Joule, who did the initial experiments on work, discovering that it took force and distance. So when you do kinetic energy and potential energy, it's also going to be measured in joules. Number 9 is sort of a trick question. It's a concept question, actually. You don't have to do any calculations for number 9. If the potential energy of a ball on top of a house is 98 joules, I'm going to write potential energy, 98. Notice joules because it's a form of energy. What is the kinetic energy of the same ball when it falls to the ground? So they're asking you to use the definitions to figure this out. So potential energy is stored energy when an object is not moving. So when that ball's sitting there not moving, it has a potential stored energy of 98. Once it starts to fall, that potential energy changes into kinetic. Because what kinetic energy is movement energy. Once it starts moving, it's now kinetic. So if you're talking about the same object, the potential energy of that object is equal to the kinetic energy because of the law of conservation of energy. Energy cannot be created or destroyed. You've probably heard that before. It's only transformed from one form, in this case potential energy, into another form, kinetic. So if I have 98 joules of potential, if I'm talking about the same object, I have 98 joules of kinetic. They're the same. So no calculation needed. And I know I asked about that on the exam, so if I'm talking about the same object, don't do any calculations. Apply this rule. All right. The world's top sprinter is running at 29 miles per hour. His mass is 92 kilograms. What is his kinetic energy? For one like this, you are going to have to solve. You are going to have to find an equation. So they're giving you miles per hour. Miles per hour are not the units we want, but miles per hour is a velocity. The mass was also given, and I already forgot what it is, 92. And they're asking for kinetic energy. So, I'm going to start by converting. And I don't have you convert on a lot of the problems on the exam because I know there's a lot of questions, but I do have a few. So just pay attention to units as you go. I want you to spend more time on solving, not necessarily converting, but I do still want you to know how to convert. So 29 miles per hour, I want in meters per second. No. I have conversion factors for you, and if you look at your conversion factors, you'll see under the chapter 2 equations is where I have the conversion factors on the very top of the equation sheet. I have miles per hour to meters per second, and I also have horsepower to watts. Those are the two that you probably would need to use in the exam. So, the conversion factor for this, miles per hour to meters per second, is that guy there. So review from chapter 1, right? When you're converting, you do this little railroad track plus sign. What goes in the top left is the number you're trying to convert. So I'm trying to convert 29 miles per hour. What's going to go here is the conversion factor. I want the miles per hour part on the bottom in the denominator. Because this horizontal line, remember, is a division line. So if I'm dividing miles per hour by miles per hour, it cancels. I'm going to put my 0.447 meters per second on top. This vertical line is a multiplication line. So to solve, I'm taking 29 times 0.447 and dividing it by what's on the bottom, in this case, just a 1. What do we get when we solve for that?
12.963.
12.963. And we're not worrying about sig figs because this isn't my final answer. That's why it's just keep them all. More accurate answer. So once you convert, you can solve. When you look up the kinetic energy equation, you only have one to choose from. So that's the one you have to use. And you are given all the variables for it. I don't think you ever have to rearrange this equation either. So I'm going to put my mass of my runner and the velocity of the runner and make sure to square the velocity. Now since this is my final answer, I am going to want to look at significant figures being just 2. Same answer. You get 7729?
Yeah.
Okay. So 2 sig figs, so 772. So it would be 77, that stays a 7, and then 2 zeros in the place of the 2 and the 9. It is energy, so joules for the units. All right. So number 11 is asking for potential energy. So what is the potential energy, PE? We only have one equation for that. So you know which one you're going to use. Makes it a little easier. They give us the mass of a clothes iron. And they're saying, what's its potential energy when it's sitting up on an ironing board? And notice the distance, or height in this case, I give it in centimeters, but in parentheses it's in meters. I do this a lot on the exam. So you just need to use the correct one. Okay, so I do the conversion sort of for you, but I want you to recognize that you would need the meters version, not the centimeters version. Okay, so I'm going to write the 0.95 meter version down because that's what I want my distance or my height in. I want it in meters, not in centimeters. Once again, that list of all your variables with the units is going to be helpful there. So PE is equal to mgh. So notice this time, for the height, for the length portion, it's not d as the variable, it's h. Okay, but that's still, that value can be used here. just changing the variables on us a little bit with some of these equations. So mass we have, that's the 1.3. G, what's this? Well, it's gravity. That object is sitting up at a high distance. The potential energy is dependent upon the rate, the acceleration of gravity when it starts falling. Okay, so gravity is 9.8. Unless I specify you're on the moon, I'm always talking about being on Earth. Okay, so 9.8 is the rate of gravity times the height, and that iron is slightly less than a meter off the ground. We're looking at 2 sig figs, and the units are going to be joules.
Yeah. 12.
12? So 12 joules of potential energy for that iron. We have one last equation, or problem, and it's a power one. So we have a 65 kilogram person climbing stairs 3 meters high in 10 seconds. So mass is 65 kilograms, I already forgot the rest of it. 3 meters high, 10 seconds. So the distance or the height, depending upon what equation I'm using, is 3 meters, and the time is 10 seconds. I think that's all it's given. It's asking for power. The power ones are a little trickier than the energy ones because you have 4 power equations, but nothing specifies what equation to use other than the variables themselves. So when you're looking at the power equations, compare them to the variables given. That's where this list is helpful, so that you can choose and narrow down which power equation you need to use. So going through, first equation, do I have force?
No.
No. So, I. The second one, I have mass, but do I have velocity?
No.
No. Third one, I have mass, gravity, it's not on here, but I always know what gravity is, so I'm going to put a check. Height or distance, yes. Time, yes. So this one works. If I want to be thorough, I can look at that last one. I don't have force, I don't have average velocity, and I don't have power. So that one's just no, no, no. So using that third one, plugging in mass, gravity, 9.8 because we're on Earth, height, 3 meters, and then the time it took, 10 seconds. So power is the work, the rate of work done. And, oh, only 1 sig fig this time. That's going to make it difficult. Power is usually a pretty big number. So 191, is that what you got?
Yes.
191. And then we only want 1 sig fig. So you see this on your calculator, just this sig fig matters. You look at the number next to it, so the 1 goes up to a 2, but then I need zeros for those remaining placeholders. So 200, and it's power, so it's watts. Power always measured in watts, no matter what power equation you use. If I ask for it in horsepower, you would have to do a conversion using that 1 HP is equal to 746 watts. But this would be the correct answer. So when you're going through the answers, even if the sig figs aren't making sense to you, pick the number closest to what your calculator says. Because I'm not going to give you 200 and then 190. Like I wouldn't do that. I would give you maybe 100 and then 200 and then 250. So just pick the one that's in the realm, even if you're not sure about the sig figs. It's a nice thing about multiple choice. You don't have to worry about the sig figs as much, because I'll kind of do that part for you. So this is not comprehensive for the exam. We only did, what, 20 questions maybe? Even less? And the exam's 50. So use this, use your practice work, the practice exam. That's another, I think, 25 questions for that guy. And using those together is really going to help.